So next we are going to start the fourth unit. So in third unit we have studied about the vibration and free vibrations, about the free vibrations and their effects and their characteristics. So now in this fourth unit we are going to study about the forced vibration. So first let us recall what is meant by vibration. So already we have seen about the vibrations in the last unit. So vibration is nothing but any motion which repeats itself after an interval of time is called as vibration. So vibration, or otherwise called as periodic motion or oscillation. So when we give a force, when any motion is there, so if it is repeating at an interval of time, then there will be some continuous motion, that is called as the vibration. So every body which is possessing mass and elasticity are able to produce the vibration. So in some machineries, rotating parts or moving parts of a machinery, there is some vibration problem. So the problems arises due to vibration. So here we have two different types of vibration. One is free vibration and forced vibration. So already we have seen about free vibration. So this is the syllabus of this fourth unit. So free vibrations are if the periodic motion or if the vibration, if continues after the cause of original disturbance is removed. That is, when we give some disturbance to a body, when we pull the body, then there is some continuous or periodic motion and we have to remove. And if we remove the force, then due to that disturbance, there will be periodic motion in the body. So that is said to be a free or natural vibration. So that is, we have to give some external force and we have to remove the force immediately. So after the release of the forces, then there will be some continuous motion, periodic motion for some time. So that is called as the free or natural vibration. So for example, we take a simple pendulum. So if we strike the pendulum, then and we have to take our hand, then it will be going on, it will be oscillating. So that is called as the free vibration. So forced vibration is when we give the external force continuously. So the force should be given, if the external force, if the body is under the influence of external force continuously, then the vibration is called as forced vibration. For example, clock, you can say the clock pendulum. So the clock pendulum, there is a continuous force, so it is continuously it is moving. So also we can say the electric bells. It's also an example of forced vibrations. So damped, in forced and free vibrations we have two different, damped and undamped. So damped means the amplitude, when there is a reduction of amplitude, then we can say as the damped vibration. So the amplitude, if it is changing, if there is amplitude is changing, then we call it as a damped vibration. Or we can say that if the vibrator system has a damper. So damper means it is able to control the vibration. So that if the damper is connected with a free vibrating body, then it is able to control the vibration. That is called as the free damped vibration. So undamped vibration means if there is no damper, we call it as a undamped vibration. So this is about the damped vibration and undamped vibration. So we can see the examples of the forced vibration. So here there is some of the 4 examples of the forced vibration. So the vibration of the floor caused by running a heavy machinery. So when a heavy machinery is on, the floor on which the machinery is placed will vibrate due to that external force, due to that force induced in the machinery. And another example, so a car when running on an uneven road surface, so if the road surface is not even, then it will be vibrating, the car will be vibrating, it will go up and down uniformly. So the reciprocating engines also due to periodic reciprocating of pistons, forward stroke and backward stroke. If it is continuous, then there will be some periodic vibrations in the body. So these are some of the practical examples of the forced vibration. So we can see about the forced vibration in detail. So forced vibration is when the body vibrates under the influence of time, varying disturbance, load or displacement or velocity, that is the external force, then the body is said to be under forced vibration. So here you can see there is this is the system. Here there is a spring. So this is the spring, mass, damper system. All the 3, spring, then mass and damper is here. So spring, mass, damper system. So here in free vibration what we did, so we give one force and we removed the force. Then due to that force, what happens? There will be some vibrations. That is the free vibration. So here we give a force that is equal to F sine omega t. So F is the external force, external periodic force, and sine omega t is that is sine theta. So theta is omega t. We are substituting theta as omega t. So the sine theta is in the form of the periodic sine wave. So it will be, the vibration will be in the form of a sine wave. That is the sine theta form. So if we give a external force continuously, so that will be in the form of a load or displacement or velocity. So then what happens? There will be some continuous vibration. So continuous vibration due to the external force. Then the body is said to be under forced vibration. So due to the influence of external force, it is called as a forced vibration. So the external force may be in the form of the load, or it may be displacement, movement, or a velocity, continuous movement with respect to time. So that is the forced vibration. So the external forcing given can be in the form of 3 types. One is periodic forcing, then impulsive forcing, and random forcing. So periodic forcing means the vibration caused may be in the form of a steady harmonic or non-harmonic load. So here you can see that. So this is a periodic forces, harmonic or non-harmonic. So here the vibration may be periodic, means cyclic. So it is repeated after regular intervals of time. That is called as the periodic motion. So for example, the periodic motion is harmonic vibration. It will be uniform. It will be in the form of a sine wave. That is, it is harmonic, means it is periodic. It is at equal intervals of time, repeated again and again. It is the periodic. So non-harmonic also can be happened. So non-harmonic means it is not perfect. It is non-harmonic. It is occurring at equal intervals of time, but it is not perfect. So that is non-harmonic vibration. So here we have two categories for periodic forces. One is harmonic and non-harmonic. So next one is the impulsive forcing. So impulsive forcing means, so the immediately there will be an external force and it will be, the amplitude will be very high, but the duration will be very short. So that is the impulsive forcing. That is, they are the short duration impact or mechanical shock by a sudden and severe application. So for example, if you give a rock explosion, then what happens? Immediately there will be some external force. Due to the external force, the vibration will be more and it will be stopped. It will be zero. So for immediate impact due to the external force with a short duration is called as impulsive forcing. For example, rock explosion and gun firing. So if there is a rock explosion, you may observe there will be some vibration suddenly and it will diminish, it will go. And gun firing also, if we fire a gun, immediately the amplitude will be more. So if you see the waveform, the amplitude will be very high at that point, then it will be zero. That is the example for this impulsive forcing. So third one is the random forcing. So random means it is not predictable. It is not predictable. That means it occurs unknowingly, or we don't know when it will occur and we cannot measure. Non-deterministic means we cannot measure that. So unpredictable, we don't know when it occurs, and non-deterministic, and we cannot correctly measure that. Example, wind or earthquake. So when there is an movement on the floor, when the land shakes, then the building will vibrate and it may cause to fall off the building. So this is a random forcing. We cannot predict and we cannot measure. That is the random forcing. So here you can see the random forces. So here the earthquake and acoustic or random forces. So the waveform is not perfect. It is randomly it is going on. You might have seen that the earthquake seismograph. It is an instrument for measuring the earthquake vibration. So that will be not periodic. It will be like this, going up and down, up and down. So that is the random forces. So it is due to wind, earthquake and traffic. So here you can see some more examples of vibrations. So forced vibration, harmonic, that is periodic vibration, is a pendulum or clock. So if we give the continuous force, continuous external force, then the pendulum goes here and there, vibrates. So that is a periodic motion, periodic forces or periodic vibration. Impulsive is rock explosion. So if a man is standing here and if it is a given explosion, immediately it will come. That is a impulsive forcing. Impulse means immediately, fraction of second, it will happen. Random means if there is a shaking on the floor, then the earthquake occurs. So wind also. So we don't know where the wind will come from, where to where it will blow. We don't know. So it is undeterministic and unpredictable. So that is about the three different types of vibration. So I hope you understand all the three different types of vibration. So this is the in our daily life we see this vibration. Washing machine, when the machine is working, there will be some vibration. it will be on the floor or in the machine due to that force. Radio, if it is on, if the radio is on, if it is working, then we can see some vibrations due to the sound. So water filter, when the water filter, when it is the sound is heard, when it is on, we see some vibrations continuously. So these are the examples of the forced vibration. So now we can see a small demo based on what is a forced vibration and why the sound is heard in guitar. Okay, we can see a small demo. So next we are going to see about the forced vibration with a constant harmonic excitation. So that is a harmonic forcing, that is a periodic forcing. So here we can consider a spring mass. So here there is a spring, mass and damper. So we can say this is a spring mass damped system. So in this system, so there is a mass here with a spring of stiffness S and this is a damper with the damping coefficient C. So this is at the initial position. So when we give a force, when we give a harmonic force, so harmonic force is this is the harmonic force. So periodic force. So it is having sine omega t. So sine theta is omega t. So since it has the sine theta, this is a harmonic force which is a periodic moment. That is a sine wave. So when the harmonic force is applied, the mass is displaced to a distance x. So the position is moved from this initial position to this position at a time, after a time t. So here we are going to solve the forces acting on the mass. So here we know there is one external force we are applying in the downward direction and we are going to see what are the other forces acting in the mass. So for that, for resolving all the forces, we have to draw the free body diagram of the mass. So this is the free body diagram of the mass. So here first, due to the spring stiffness, there is one spring force acting. So this is S is the stiffness and X is the displacement. So Sx is the spring force. So spring force is acting in the upward direction. Next, this is the external force, that is a harmonic force which is acting in the downward direction. So next we have the damper. So there is a force, damping force. So it is acting in the upward direction. So the value will be equal to C into dx by dt. So this is the damping force. So C into dx by dt is the damping force acting in the upward direction. So since the mass moves downwards, so there is an inertia force acting in the direction opposite to the direction of the movement. So movement is downwards. So the inertia force acting upwards. So what is the inertia force? Mass into acceleration. So mass m. Acceleration is, so this is a displacement. So due to this displacement, the acceleration is written as d square x by dt square. So this is the acceleration. So this is inertia force. So now we have 4 different types of forces and we are going to resolve all the forces. So first is inertia force acting upwards, damping force upwards, then spring force upwards, and the external disturbing force, or we can say impressed force or external disturbing force, it is acting in the upward direction. So now we are going to resolve this. So in the engineering mechanics, we know the direction of forces. So always the upward forces we take as positive and the downward forces we take as negative. So except this external force, all the forces are positive. So we have to apply the D'Alembert's principle. For resolving all the forces, we apply the D'Alembert's principle. What is D'Alembert's principle? The inertia force and the summation of all the external forces is equal to 0, or it is in equilibrium. So inertia force m d square x by dt square plus external forces. What are the external forces? Damping force, then spring force and harmonic force. So all the forces are positive except this force is negative. That is equal to 0. So m d square x by dt square plus c dx by dt plus sx, take this to other side, f0 sin omega t. So for easy simplification, I divide by all m. Divide all the terms by m. So d square x by dt square plus c by m dx by dt plus s by m into x equal to f naught by m sin omega t. So this equation is called as the characteristic equation of the damped forced vibration, or we call it as a governing equation. So this equation is seen to be a linear one, non-homogeneous, and it is a second order differential equation. So for finding the solution of this equation, of this differential equation, we have one method. So we have to find the solution in the two parts. We can find the solution into two parts. One is the complementary function and second one is the particular integral. So this, by this we can find the complementary function, and this is through this we can find the particular integral. So the complete solution is equal to x complementary function plus particular integral. This is the complete solution. So first we can find the complementary function. So to find the complementary function, first we have to take this part alone. So we have to consider the RHS term as 0 and we have to take the LHS alone. So in this equation, so already we have seen the derivation in the previous free longitudinal system, longitudinal vibration system. We have seen this derivation. So same derivation is, so same answer we can use for this also. So the complementary function is equal to x e power minus zeta omega n t sin omega d t plus phi. So this derivation already we have seen in the third unit. So the same answer is taken here. So xc equal to x e power minus zeta omega n t sin. So we can write this as root of 1 minus zeta square omega d t plus phi. So it can also be written like this. So this value is the complementary function. So keep this equation. So next we have to find the particular integral function. So to find the particular integral function, here we have seen we are going to use a method, that is, so we are going to replace c by m as a, then s by m as b and f naught by m as d. So d square, so here c by m, so it is a d plus b, here it is s by m b equal to, here for d f naught by m we have replacing by d sin omega t. So this equation. So particular integral we are going to find d sin omega t. So divided by, so this equation you have to write, so d square plus a d by plus b. So for d square we have to substitute as minus omega square. I hope you have studied in this part differential math equation in the first year. So I am saying the steps you follow. So minus omega square plus a d plus b. So now we are going to form an equation. So b minus omega square plus AD form this. So we have to take this and we have to multiply the complementary function. So minus minus. So b minus omega square minus AD. So simplify this. So a square plus a plus b into a minus b. So a square plus b square. So simplify this. So after simplification, you are going to substitute b minus omega square as a cos phi, and a omega is taken as a sin phi. So the constants a and phi are given as a equal to root of b minus omega square whole square plus a omega the whole square. So and tan phi. So this is tan phi, and phi is equal to tan inverse of a by b minus omega square. So substituting the a value and phi value, we get the partial integral, this answer. So the final answer we get for the partial integral equation is f naught by sin omega t minus phi by root of s minus m omega square into the whole square plus c omega whole square. So I have written the derivation. So the derivation is not that much important. So you understand the derivation step by step. So the answer I have shown here. So for problems we need this answer. So f naught by root of s minus m omega square whole square plus c omega the whole square sin omega t minus phi. So this is the value of the particular integral. So next we have completed the complementary function and the partial function. So we are going to write the complete solution. So to obtain the complete solution, so add the complementary function and the partial differential function. So this is complementary function, this is partial function. So this is a complete solution for this system subjected to the sinusoidal excitation. So here the constants x and phi 1 can be determined from the initial conditions. So first we can see that the system begins to vibrate at initial conditions, and the x and phi 1 value can be determined from the initial conditions. So you can see here. So we are applying the force. So the time starts, this is a continuous force. So first initially the time increases from 5 seconds, 10 seconds, then 1 minute, 2 minutes, 5 minutes, 10 minutes. So continuously the time is going. So the time is ending up to infinity. Up to infinity it will go. So we are going to replace the time. So time tends to infinity. So when time tends to infinity, so the value of this function, that is e power, it becomes e power minus infinity. So if it becomes e power minus infinity, then this term becomes 0. So initially there will be some value based on the constants x and phi 1. Initially there will be some value of the function. So as time goes by, when the time is increased, then this term becomes 0 and the whole term becomes 0. So now the displacement is given as x equal to f naught by root of s minus m omega square the whole square plus c omega the whole square into sin omega t minus phi. So this is the displacement of the system, which is given by the particular integral only, because this term becomes 0 when time goes by. So this equation shows that the motion is simple harmonic with the circular frequency omega. So this is the displacement equation. So with this equation we can find the displacement of the system. So next we can find the phase lag. So when the displacement, when a force is applied, so there is some displacement. So the displacement vector, it lags by some angle. So it varies by some angle. The displacement varies with the angle. So that angle is known as phase lag. So in other words, we can say that the phase angle, it is the phase lag by which the displacement vector lags the force vector. So when the displacement vector lags the force vector, it is called as the phase lag. So already we have seen the formula, that is we have substituted tan phi equal to A by B minus omega square in the previous derivation. So that part I am taking. So tan phi equal to A by B minus omega square, where A is C by M and B is S by M. So I am substituting the A, B. So also since we know C is equal to 2 zeta into S by omega n, and omega n equal to root of S by M. So we are also substituting for C and omega n, and we got the answer phi is equal to tan inverse 2 zeta r by 1 minus r square. So where r, we have substituting for r is omega by omega n. That is called as the frequency ratio. So the frequency ratio is called as the r, is substituted as r. So it is omega by omega n. So using this formula we can find the phase lag phi. So in this equation, that is in the x max, that is maximum displacement formula, if the damper zeta, damper coefficient zeta is 0, then we can write the x max as f naught by s by 1 minus r square. So in the formula x max, so in this formula you can see in this formula, so if zeta is 0, this part will be completely 0. So this part is completely 0. So we get the formula, that is f naught by s by 1 minus r square. So that is the formula we get here. So also we can write x max equal to f naught by s 1 minus r is omega by omega n. So omega by omega n the whole square. So if you take LCM, if you take this omega n square to the numerator and we substitute for omega n, it is root of s by m. So omega n square, it is s by m. So substitute and find the last answer is f naught by m. So s will be cancelled. So f naught by m by omega n square minus omega square. This is also a formula for x max. So using the given values, you can find the displacement. If mass is given, you can use this formula. If the ratio is given, frequency ratio is given, you can use this formula. So this is various formula for finding the displacement. So this is also called as the amplitude. So if you want to find the amplitude of vibration, that is the maximum displacement. So maximum displacement is the amplitude. Both are same. This is the amplitude. So if in the problem, if they ask to find the amplitude, if they give the stiffness, then the ratio, frequency ratio and the force, if they give the given data, and if you ask to find the amplitude, the same formula. This is x max is nothing but the amplitude of vibration. So next we can see the response of to the periodic forcing. So in the graph we have seen the complete solution for the spring mass damper system in the previous derivation. So that is, this is a complementary function and this is the particular integral function. So both the function together we write as a complete solution. So in this based on this formula, we are going to give the two response here. So that is, one is the transient vibration, another one is the steady state vibration. So here in this formula, so this part, first part is the complete, that is a completely, it is denoting the first part is the complementary function. So in this function you can see already we have seen that, so initially the system has a natural frequency omega n. So when the force is applied, that is the harmonic force, when a sinusoidal harmonic force is applied, what happens at the time increases. When the time increases, then initially there will be some value, but when the time increases, when t is increased until infinity, what happens? So this part, that is the e power, it becomes e power minus infinity. When t tends to infinity, it goes on up to infinity level, then that means e power minus infinity, the term will be 0. That means the completely this term will be 0. So initially there will be some value, some frequency value, but when time goes on, the value, the first part becomes 0. So it is called as the transient vibration. So first you can see this, the complete solution. The first part is the complementary function. So the complementary function, it becomes negligible, or we can neglect that when the time tends to infinity. That means e power minus infinity is 0. So the vibration of the first part is called as the transient vibration. So first part of the vibration is called as the transient vibration. So this occurs at the damped natural frequency omega d of the system. So initially you can see with the complementary function. So initially it is when time is equal to 0. When the time is 0, the value is there. There is some value. And when time increases, what happens? So the frequency, the amplitude decreases and it tends to become 0. So this part, that equation itself becomes 0. So this variation is called as the transient vibration. So this is a first response of the periodic forcing. Second part is this is the second part, that is the particular integral part. So when we take this part, this part, if it becomes 0, then the next part is taken. So the next part you can see, the second part is the particular integral function. So in the formula you can see there is a sine theta, sine value. So it will be a constant amplitude. So in this it is seen that the sinusoidal vibration is a complemental amplitude, that is a constant amplitude. It's a constant amplitude in this second part of the integral function. So this vibration is called as steady state vibration. So this vibration, it occurs at the frequency of excitation of the system. So after the transient vibration, it dies out, that the complete solution has the steady state vibration only. So first we have the transient vibration. First there will be some amplitude, and when time goes by, the frequency is reduced and it becomes equal to 0 when the time tends to infinity. Okay, so this is when this transient vibration dies out, then the steady state vibration will be there. So the complete solution has the steady state vibration only. So steady state vibration means it is a periodic vibration. So when you combine both the transient and steady state, you can see. So for some part you can see this is a transient. For some part it is from this to this part, it is some transient vibration, not correct steady state. So after time pass by, after this transient vibration dies out, it becomes a complete, it's becoming a steady state vibration only. So that is the solution for this response. So we have two response. Initially there will be transient vibration, and after transient vibration dies out, then the steady state vibration only will be there in the solution. So next is the magnification factor. So magnification factor, or otherwise we call it as a dynamic magnifier. So here the ratio of the maximum displacement to the static deflection to the static force, that is the zero deflection, zero frequency deflection, is called as the magnification factor. That is the maximum displacement, and the zero frequency deflection is called as the magnification factor. So we know the formula, that is a maximum displacement or the amplitude of the forced vibration. So they can ask maximum displacement also same formula, and amplitude also the same formula. So we have the formula x max equal to f naught by s by root of 1 minus r square the whole square plus 2 zeta r the whole square. So that is equal to, so f naught by s can be replaced by zero frequency deflection x naught. So if x naught is taken this side, x max by x naught is equal to magnification factor. So this is the formula for magnification factor, that is x max by x naught, maximum frequency by zero frequency deflection, that is the magnification factor. So here the magnification factor formula, you can see this. So here it is written as x max equal to magnification factor into x naught. So in this magnification factor formula, it is clear that the magnification factor depends upon two things. One is the ratio of the circular frequencies, that is the omega by omega naught. What is omega by omega naught? It is R, frequency ratio R, and damping factor zeta. So this factor, magnification factor, depends on R and zeta, it is damping factor and ratio of the circular frequencies. This is omega by omega n. So this is the magnification factor. So here from this we write the two conditions, that when zeta, when there is no damping, then zeta will be 0. So remember, damping coefficient or damping factor means it is zeta. So when zeta is 0, that is when there is no damping, then this part becomes 0. So the magnification factor will be 1 by this square, and this root will cancel. So 1 by 1 minus r square. So this is for zeta equal to 0 when there is no damping. So at resonance means that both the frequency will be equal. There is a natural frequency and the amplitude frequency will be equal. So that is the condition is r is equal to 1. If r is equal to 1, then the magnification factor will be, substitute for r is equal to 1, that means 1 by, it is 1 by 2 zeta equal to s by cw omega n. So 2 zeta is equal to c omega n by s. So from this we can write the magnification factor. So this may be, they may ask in 2 marks. So the formula, or they may give any values and they may ask to find the answer. So here S is the stiffness, C is the coefficient, that is the damping force, and omega n is the natural frequency. So using these formulas you can solve the problems for magnification factors. So next we can see the two characteristic curves. So here we have the frequency response curve and the phase frequency response curve. So this is a frequency response curve. So we draw a response curve for magnification factor in the y-axis and frequency ratio in the x-axis. So that is a frequency response curve. So you can see the various values are plotted. So zeta value, when it is higher, then zeta value is very small. So when the zeta is more value, then it is lower than the it is lower at the smaller damping values. So from this we see so many observations. From this we have seen so many observations. That is, So for higher values of damping, so this is the higher value of damping, almost high. So the higher values of damping lie below the lower values of damping. So these are the lower values of damping. So the higher value is lying below the lower value of damping. So at zero frequency, this is zero frequency, so the magnification is unity. At zero frequency, the magnification is unity. That means the damping has no effect. So at the higher frequency, when the frequency is higher, so the magnification tends to be 0. So at higher frequency, the magnification tends to go into 0. Or we can say the amplitude is very small. So it tends to 0 amplitude. So the amplitude of vibration is becoming very small when magnification tends to 0. So also at resonance, when R is equal to 1, you can see that the amplitude is becoming very excessive for small damping. At R is equal to 0, the small damping has more amplitude, excessive. This high part, no, this is the amplitude. So it is having high amplitude for lower or small damping values, and hence it is decreases with increase in damping. So when the damping increases, the amplitude decreases. So this is the observation we see from this characteristic curve, that is frequency response curve. So next is the phase frequency response curve. So in this curve you can see that the frequency ratio and phase angle is plotted. So here we have different damping coefficients. So in this graph we have 3 observations. That is at low frequency. So at low frequency the phase angle is 0. So when the frequency is low, the phase angle is 0. That means here the that external force or the impressed force, it balances the spring force. So the external force balances the spring force at this part. When the phase angle is 90 degree, when phase angle is 90 degree, you can see this is a resonant frequency. That is R is equal to 1 is the resonant condition. So resonance condition is R is equal to 1. So at R is equal to 1, we get the resonant frequency. So at resonant frequency, the phase angle is becoming as 90 degree. So that means the impressed force or external force balances the damping force. This is the second observation. Third observation, at high frequency, when the frequency is very high, the phase angle is 180 degree. 180 degree at high frequency. That means the impressed force balances the inertia force, that is opposing force. So here we have 3 conditions. So at low frequency, then at resonant frequency, you can see that at resonance the amplitude is high. The amplitude value is high at resonant. So resonance we have 2 conditions. One is R will be equal to 1 and the amplitude will be very high, excessive. So these are the 3 observations we see from this phase frequency response curve. So next we can see some problem based on this formulas. A mass of 50 kg is supported by an elastic structure of total stiffness 20 kN per meter. Mass M is given, stiffness S is given. The damping ratio of the system is 0.2. So damping ratio, that is zeta. A simple harmonic disturbing force acts on the mass, and at any time t seconds the force is 60 sin 10 t newtons. So 60 sin 10 t, that formula is F naught sin omega t, that is in the form of F naught sin omega t. So this is F naught, this is omega. From this we get 2 values. Find the amplitude of the vibrations and the phase angle caused by the damping. So we have to find the amplitude, that is x max, and phi. phase angle. So first, before finding the amplitude, this is the formula for amplitude. X max equal to f naught by s by root of 1 minus r square whole square plus 2 zeta r the whole square. So here f naught is 60. S is given. R we have to calculate. Omega is given. Omega n we have to find out and find out r. Then zeta is given. That's all. So omega n is equal to root of s by m. So s is given, mass is given. So if it is kilo, we have to put 10 power 3. Otherwise we can leave it. So r we have to calculate. Then find the x max. So substitute all the values here and find the x max. So x max is 3.865 mm. Next, phase angle. Phi is equal to tan inverse of 2 zeta r by 1 minus r square. So all the values are given. So find the answer, 14.93 degree. So this is a direct substitution of the formulas. So next problem we have, a mass of 50 kg is supported by an elastic structure of stiffness 20 kilonewton per meter. Mass is given, stiffness is given. A simple harmonic disturbing force in newtons expressed as 75 cos omega t, 75 cos 12t, acts on the mass. So we know that the sign formula only, it is a simple harmonic disturbing force, but here in the problem they have given cos. So anyhow the cos function also, it seems to be a simple harmonic function only. So we can use this for our problem. So this is f naught, this is omega. So f naught cos omega t. If t is expressed in seconds and the damping force is 0.25. So zeta is given 0.25. So find the amplitude of the vibrations and the phase angle caused by the damping. So we know all the values. So here using this we can find out similar problem like a previous problem. So we can find out the x max, maximum displacement or amplitude, and phase angle also. So you can use these formulas, omega n, then phi, then this is for amplitude. So using omega and omega n, you can find r. So you can use this r formula also. So this formula also you can use. Then that r formula, this also we can use. So find out the answer. It's the same procedure only. So you solve this problem by yourself. So we can see in the next class.